أهلا بكم. أهلا في أول سيمينار أكاديمي منظم تحت اتحاد الدارسين والمصريين بجامعة تورونتو. Welcome to the first academic seminar organized by the Egyptian Student Association at the University of Toronto. السيمينار ده احنا منظمينه عشان نتبادل الأفكار والأبحاث بين الناس اللي بيدرسوا في جامعة تورونتو مع بقية العالم من خلال صفحات الإنترنت. We organized this seminar to discuss our research projects, our very exciting research projects at the University of Toronto, and with everybody else on YouTube and on other social media websites. في الحقيقة في كوادر مصرية كتير بتدرس في جامعة تورونتو، منهم الدكتورة اللي هتتكلم النهارده. وعايزين السيمينار ده يكون لينك ما بيننا وما بين الناس اللي في مصر وفي العالم العربي وبقية العالم عشان نناقش معاهم البحوث بتاعتنا على مستوى أكبر إن شاء الله. النهارده عندنا باحثة مصرية استثنائية تقدم لكم شغلها وقت الدكتوراه. الدكتورة سماح الطنطاوي مدرس مساعد في جامعة القاهرة كلية هندسة، وحاصلة على بكالوريوس من كلية هندسة قسم اتصالات سنة 2004 ومن قسم رياضيات ماجستير سنة 2007 الاثنين تحت دفاع مرتبة الشرف. So the speaker today is Dr. Samah El-Tantawy, a professor or an assistant professor at the Cairo University and also a postdoctoral fellow at the University of Stuttgart. The University of Toronto, sorry.
Teaching assistant, by the way.
I'm sorry?
Teaching assistant, by the way.
Teaching assistant.
Cairo University.
Teaching assistant at Cairo University. And she got her Bachelor of Science and Master of Science from the Cairo University as well in Engineering Mathematics and in Communications Engineering. She got her PhD from the University of Toronto under the supervision of another Egyptian professor, Dr. Baher Abdelhai. درست دراسات الدكتوراه في جامعة تورونتو مع دكتور مصري آخر اسمه دكتور باهر عبد الحي في الانتليجنت ترانسبورتيشن جروب أو منظومة المواصلات الذكية، وحاصلة على عديد من الجوائز منها ال IEEE ITS Best Dissertation Award والجورج دانستينج PhD Dissertation Award كمان. رحبوا معايا بباشمهندسة سماح.
For this introduction, and thank you all ESA executives for the invitation. It's my pleasure to participate in this exciting and inspiring event, and thank you all for coming. I prefer to talk in English given that the presentation can have some technical terms, so it's better to have all the speech maybe or the presentation in English. So today I'm gonna present my research work, my PhD work, and we are currently still working in the same project of developing multi-agent reinforcement learning for integrated network of adaptive traffic signal controllers, which we call it Marlin. And this simply, as the title shows, smart traffic lights that learn. This work was under supervision of Professor Baher Abdelhai. And so, in order to start, I'm going to give you a brief overview of Marlin. What's Marlin? And before saying what's Marlin, why is Marlin? Basically, traffic congestion is one of the problems that we all suffer from, and it needs no introduction. It has all the negative impacts on society, environment, economy. It actually costs Ontario alone $6 billion annually, and it's rapidly spreading in all medium to large cities worldwide. And large part of this traffic congestion comes from the excessive delays at intersections. So our proposed solution here is Marlin, which actually works as a brain at the traffic light that's based on artificial intelligence, which enables traffic lights to self-learn and self-control with the neighboring traffic lights. And also it works with all the safe options and backup modes by integrating this software with the existing traffic controllers in the field. And the benefits that we got from Marlin based on simulation results so far are 40% less delay and 95% less money spent on infrastructure expansions, about from 20 to 30% savings in CO2 emissions, and of course the stress savings is priceless. So first, I'm gonna start with a brief background of the adaptive traffic signal control problem, and then I'll highlight the objectives and the design features for modeling, and then we'll discuss the framework. We'll also discuss the results for different applications, and we'll talk a little bit about one of the recent projects about developing hardware in the loop simulation for evaluating the integration with the hardware, and then we'll have a good conclusion and future work. So, as I mentioned, traffic congestion as a problem. It can be solved using either long-term solutions by planning or expanding the infrastructure, or short-term solutions by enhancing the operation of the existing infrastructure using intelligent transportation systems. That includes advanced traveler information systems, advanced traffic management system, advanced public transit systems, and others. And the different strategies can be implemented for advanced traffic management system. One of them is signal control that actually has three main types. One of them is fixed time control, which is the common use system, by the way, in most of the intersections around the world, where the timings, the green time and the red time for each direction or group of movements are calculated or optimized based on historical data, volume data, and it's not changing with the fluctuations in traffic. Actuated control, where there is loop detector under the vehicle that sends the traffic and sends calls. Each vehicle past this detector sends calls to the traffic light, and then it can, if the green for certain movement is on, then once this call is received, the green will be switched to the other movement. So it works good, but for light traffic, however, the most advanced system is the adaptive control system that works based on optimizing these timings for the traffic light in real time based on the fluctuations of traffic in order to achieve certain objective, which is, for example, minimizing the delay or the waiting time of vehicles approaching the place. The adaptive traffic signal control went through several generations, starting from transit that was kind of fixed, mix of the fixed time and actuated, and then there was SCAD system that's still actually implemented in many areas, especially in Europe. The optimization is done offline, also based on historical demand data, but the change is done based on this control policy that's calculated offline in a centralized way, which means that all the instructions or the commands for the traffic lights comes from a traffic management center. And SCOOT, which was the next level or generation, is also centralized, but it does the optimization online. And then there is the next level was based on distributed or decentralized. However, they rely on a method called dynamic programming, which is a model-based method. It requires to describe or model the traffic environment or traffic flow by having all the transition probabilities from one traffic state to the other, which is very difficult to be accurately modeled in case of the stochastic traffic flow model. And also it has suffered from the curse of dimensionality. When the number of intersections grows, so it grows, the computation time grows exponentially and so on. So finally, the development or the evolution for the adaptive traffic signal control goes towards using self-learning control and at the same time, of course, distributed or decentralized. So to summarize the limitations of the previous generations for adaptive traffic signal control, they are centralized, which requires massive, expensive communication network from the central to the intersections, the controlled intersections. It's model-based, relying on an accurate traffic modeling framework. It suffers from the curse of dimensionality, and also it requires human intervention and require highly skilled operators to deal with the parameters of these systems. So in a nutshell, the adaptive traffic signal control problem, the main challenges are that each intersection affects the others. And In order to solve the network as in one shot, this requires central computer or computation, which is interactable theoretically and too complex in practice. So the solution is to have a decentralized system or agents that learn to control their local intersections and also learns to collaborate. So the main, it's, as I mentioned, Marlin is based on artificial intelligence technique called reinforcement learning. And it mimics how human beings are learning in their life. So, for example, if there is if a child wants to learn how to walk for the first time without a teacher, or he might fall at the beginning in his right, for example, and then he will know that this is not the best action to do based on the reward that he got, and then he will take another action, he might fail again in his left, and then with few iterations, he will learn how to walk. We use also another example for this poor little mouse here that tried to navigate this maze in order to achieve this cheese, and with trial also, based on knowing the state of his internal state and taking the action, and based on receiving the award, it will learn with iterations what's the fastest way to achieve its reward, which is the cheese. Similarly, in the traffic environment, the agent here is the controller that controls the traffic lights. Based on observing the traffic state or queue length at different approaches, this agent will take an action that will affect the environment. This effect will be measured in a form of reward value, for example, the savings in delay, which is the cheese here, and then update the control policy, which is the mapping between each state and action based on this reward value. And keep doing this until the agent learns what's the optimal mapping between each state and action. And usually this process of learning until at least it becomes, for example, an adult or something, it happens using simulation. And then we go to street and continue learning also and updating the policies. So again, the challenge is this was for one agent and for one intersection. When it comes to having a transportation network of different intersections or multiple intersections, the challenge is that these agents are learning simultaneously. So we call the environment in this case is non-stationary, which means that the effect of the agent's action is it doesn't only depend on this action, it also depends on other agents as well. So each agent is faced with a moving target learning problem, and that's why it needs to have a coordination between the agents. So the analogy between the problem for single agent and when we have multiple agents, in the single agent case, the environment is stationary, which means this can be, for example, for an isolated intersection where the other intersections are very far away. So in this case, the mathematical modeling for the problem is to be modeled as a Markov decision process, where the solution is to find the optimal control policy, and the algorithm that gives us the optimal control policy is the dynamic programming methods. But again, this method suffer from that it requires model for the environment, and also suffer from the Kelser dimensionality. And so the model-free algorithm that achieve as much as the dynamic programming without suffering from the other limitations is the reinforcement learning. And similarly, in the multiple agents environment, which is a non-stationary environment, the mathematical framework or modeling is a stochastic game. We have different layers of decision makers that affect each other, and the solution is to find the optimal equilibrium joint policy, and that there are some approaches, game theory approaches, that rely on having a model also for the environment, and also exponentially increasing with dimensions and so on. But the multi-agent reinforcement learning approach can solve this problem without having a model for the environment. Are we the first ones to solve the problem using multi-agent reinforcement learning? No. In the literature, there are some studies that consider reinforcement learning to solve this multi-agent problem. However, they have some limitations. Most of them, they have specific design for reinforcement learning in terms of defining the state, the reward, and the action. And also they have used very simple traffic models that has so many assumptions. And also most of them also didn't test on a realistic demand and realistic network. And most of them, which is the main limitation here, didn't use efficient coordination approach. They mainly they assume it's stationary environment and they deal with each agent as an independent agent. And on the other hand, the literature of the theory itself, the multi-agent reinforcement learning, relies on having full observability requirements, which is not guaranteed or is not practical in the transportation network or transportation problems, because they always define the game by the state of the game, so which is the state of the transportation network. So this is one of the limitations, and which makes them suffer from the curse of dimensionality as well. So in Marlin, we propose Marlin to be working in two modes, independent mode or coordinated mode, in order to be generic. And in the coordinated mode, we have used one of the approaches in the literature for multi-agent reinforcement learning with coordination, but with also considering the locality of interaction principle, which is basically that each intersection cares only about the neighbors, the surrounding neighbors, the adjacent neighbors, and each one of these neighbors cares about the neighbors in a cascading fashion. And finally, modular Q-learning, which is where we have the decision making at the end for each agent to take the best response action based on all these neighbors, or based on the estimate of models for these neighbors. So in the independent, again, it's just repeating, there's an independent mode where each intersection only cares about its own, the Q length as a state, the delay as the reward, and the action is to either extend or to switch to another phase and so on. Or coordinated where the intersections share their information and update their models, the models for the neighbors, and act accordingly. And here, this is one of the main advantages or features for Marlin over the other systems. That the coordination here is in two-dimensional network. So each intersection, as I said, consider the neighbors, and each one of the neighbors consider the neighbors, and so on. It helps minimize the delay in the transportation network overall, while the other systems that use the word coordination in their systems, they rely on having a green wave or synchronization along an arterial in order for each car to just pass all the intersections without stopping at any of them. So they call this parameter that works as a master clock to help achieving this green wave offset value, but we use a totally different concept of coordination in a network-wide, with a network-wide coordination. So the overall framework consists of three main components: the agent, which is responsible for the learning and decision making; the environment, which is responsible for observation and acting. And here actually we use a microsimulator, traffic microsimulator called Paramex, and the interface module that synchronizes the interaction between the agent and the environment. And of course, all these modules, the input for the input parameters for these modules are exogenous to the system, so it's designed to be generic to solve actually any kind of problem, even if it's not adaptive signal control at all. So this agent is for any decision-making problem that has the same features of the traffic signal control problem. And so I'm not going, of course, to get into details about this, but I just want to highlight that there's an independent mode, an integrated mode, and even in each one of these we have tested different algorithms or techniques. So the main design features for Marlin include that it's self-learning, which doesn't require human intervention, and it's decentralized, which has different advantages over the centralized system, robustness, the scalability, and it's also less expensive. And model-free doesn't require the accurate model for the environment that's difficult to be modeled. And also it has the coordination in a network-wide, and it's scalable, so insertion or the deletion of any intersection is much easier than the centralized system, and also it's pattern sensitive, doesn't require prediction models, and it's developed to be generic to work in any different mode of operation. So the applications, we tested Marlin in different test bed networks. First on an isolated intersection or one intersection, in order to test different RL design parameters, state, action, reward. And then we've tested on 5 intersection network to test different coordination methods. And finally, on a large scale application to also test the scalability of the system. So the intersection that we consider is Bay Street and Front Street intersection. And we usually get the counts from City of Toronto. And we built a simulation model, and we consider 2 cases actually. One is uniform demand arrival, where there's same amount of vehicles arriving to the intersection in every 5 minutes, and variable arrival profile, where the amount of vehicles arriving, although the total is the same, but the amount in every 5 minutes is different in each approach. So here we have 4 different arrival profiles, because there are 4 group of movements for this intersection. And we tested different state definitions, for example, to just consider the queue length, or consider the arrivals in the green direction and the queue length in the red direction, or to consider as the state definition the cumulative delay, and also different rewards, different actions, and so on. And based on this experiment, we found the best set of design parameters are this set here. And this results from comparing the system Q-learning here, which is the reinforcement learning method, with the fixed time and actuated control methods. And the main point here is that when we consider, this is the gray column here shows the arrival flow, which is in the uniform case. The amount of green is shown here in these curves for the 3 systems, the actuated, the fixed time, and RL. And so there are similar amount of green allocated for each in each 5 minutes for this specific approach. However, in the variable demand profile case, the amount of green also in using the reinforcement learning method, the amount of green varies similar to the arrival flow in this movement. In the 5 intersection network, we just extended the network around this intersection, Bay and Front, including the 4 surrounding intersections. And we have tested 2 scenarios, normal traffic conditions and oversaturated conditions, where we increased the demand by 50%. And also we have different benchmarks, the pre-timed, actuated, and the independent mode and the coordinated mode. And one of the observations here is that when this is the travel time for different routes, this route 1, for example, going from northbound, and this route 2, and so on. The route number 5 actually here for the vehicles originated in this point here and going through 2 intersections. to the destination here. And this, we found that the most savings happened in this route because there are the demand was high that's going through the left turn here and the other left turn here. And the coordination between agents helps these intersections to know that if there is a queue spillback in the downstream intersection, so the intersection knows automatically that it will meter the traffic, or it will not let so many traffic goes to the downstream intersection if there is a queue spillback. So in the large-scale application, we tested the system on a network of the lower downtown core of Toronto that has about 60 intersections. And also the results were very promising compared to the base case, which has actually mix of fixed time control, actuated control, and there are some adaptive control that we tried to approximate how they are working, but given that they are commercial systems, so we don't know the exact details of how they are developed, but we did our best to approximate these systems, and this was the base case. And we found the savings in average delay per intersection, was about 38%, and in the average queue length per approach was about 32%. And also important that there is balancing for the queue length in different approaches. So the standard deviation for average queue length was about 31%, the savings. And also we did have a special distribution for these savings to see what are the areas that warrant the adaptive traffic control, and especially Marlin compared to the other systems, which will help municipalities or city to identify the locations that needs investing or changing the system and updating it with another kind of adaptive control system. So we found that there are some areas that warrant this system more than others, and it was expected that they are around the freeways from the Gardner here, or actually the areas that has dense economic and business activities, like this area here. And also another important observation was that when we were measuring the travel time along different arterials or corridor, we found that the coordination helps not only minimizing the travel time, but also minimizing the variations of the travel time along the simulation hour or the AM peak hour. This simulation is done for the AM peak hour. So, which makes it more reliable to travel if we use the Marlin C or coordination. And not only this, but here, this is the Gardner eastbound. So it doesn't have any signals, right? But the improvement here happens because it was expected that when we improve the downstream capacity or the surface streets, this will affect positively the performance on the freeway as well. And actually, after finishing this was the thesis, all the applications before, but City of Burlington were interested to test the system with collaboration with a company called SEMA Plus and University of Toronto. So this joint project was to test Marlin on 2 different locations in City of Burlington, where these intersections are really chronic in terms of the high demand and the congestion in these areas. One of them is Walker Line and Harvester Road, and the other one is Guelph Line and Harvester. And the results were very also promising. And there's also here an important observation. We found that, for example, in the first network here, we usually model not only the chronic intersection, but the surrounding ones as well. So in the case of Walker Line and Harvester, we found, although we found savings in the speed savings and travel time savings and CO2 emission, but comparing the Marlin in the independent mode and the coordination mode, there was no significant improvements from using the coordination over the independent. So in this case, for example, we don't need to have the communication between the intersections, we just need the independent mode. On the other hand, the other network of Guelph line and Harvester route, we found that using these results are using the coordination mode of Marlin has improvements of over the independent mode, so coordination here was necessary. Actually, the other alternative was proposed by the city is to have an expansion by building a new lane in each direction for this experiment here, which will cost the city millions of dollars. So that's why the number of 92 savings in infrastructure expansion comes from compared to using Marlin that will cost for the intersection about $20,000 to $30,000. So again, to summarize the benefits of Marlin. So for the end users or travelers, based on simulation results, the savings is up to 40% on average in delay, and about 25% in travel time, and 30% less in CO2 emission. We actually used specific models to measure the CO2 emission in traffic simulators, and less traffic variance, travel time variation, which means better reliability. The benefits, on the other hand, for the urban traffic control management departments or the cities, the municipalities, which are the customers for such kind of systems, is that it requires lower capital cost because it needs inexpensive communications, and also lower operational cost due to the reduction in human intervention and scalability, given that it's self-learning system. So the next step was when we're talking to municipalities and cities about the system. So how this will work with the existing infrastructure or the existing controllers. So the next step was to test it using actual hardware, the off-the-shelf hardware controllers that are already in the cabinet, and see if we can do this integration using our software. This project actually was done as a teamwork, as you can see here, with other colleagues. And so the idea is that we have Marlin on an industrial or embedded computer, and it overrides the controller operation by sending the commands to, as I mentioned, override the controller operation. And there is a controller interface device that was developed in order to test the effect of the actions on the simulator again. This is one step forward, but again before the field implementation. So it's called hardware in the loop simulation, and we tested this system, and we also found the same results, which was expected. So the components that are required for field testing is an internet switch that can facilitate the communication between the industrial computer that runs Marlin, the traffic controller, the cameras, and the neighboring intersections. So another one step forward was to look for a partner, given that we are only developing a software, and for the customers it's very hard to convince them with a software without having like a company that is already, they know their name or their brand to rely on that. So the venture party here, or partner here, was Peak Traffic Corporate. So as I mentioned, it's important to have for this kind of product a partner that has field experience, credibility with customers, and sales network, and they have all the backup modes and fail-safe mode. And Peak actually, alhamdulillah, has all these advantages, and they show interest of the system. They have about 1/3 of the traffic signal control market share, over 50 distributors, and they have half of the traffic lights in Toronto operated by peak controllers. And they were seeking an adaptive traffic signal control at the same time that we were approaching them. So we think that it's a perfect partnership, and we hope it will be. And so the plan that we went through, the development of Marlin, the 2000 here, because my supervisor, Professor Bahir Abdelhai, started the work of reinforcement learning in traffic signal control back to 2000 actually. So the main contribution of my work is to investigate the game theory part and to develop the software itself and test it on a more realistic network. So this year was the integration with peak controller, or actually 2012-2013 was the hardware in the loop simulation project and the partnership with peak. And hopefully next year we will have the first field operation test, inshallah. And from there we can have field implementations after hopefully it will be successful in different places around the world. So in summary, Marlin, we see Marlin as a state-of-the-art and fourth generation for the adaptive traffic signal control that's thoroughly developed and tested, and patent is pending so far. So yeah, the ongoing work is to have a potential field operation test and productizing the Marlin. And in terms of the research, we need to do some work in having this should be transit signal priority. It's common in signals that when a transit vehicle comes, so it has the highest priority and the green should be switched to this movement. But we are proposing a new definition for people priority. So based on the number of people in the bus, given that we have the technologies hopefully in the future that can give us this information, we can minimize the people in the intersection, whatever is transit vehicle, like regular cars, or even pedestrians. So this in terms of the future research. And at the end, thank you for listening. I'm happy to answer any questions if you have any.
No, go ahead. I was just wondering about the risks that are involved in such a smart, like how smart is that?
So yeah, again, it's maybe this was in the first slide here, that given that we are integrating with a traffic controller, hardware controller that's already has all the safe modes, that if the system for any reason the cameras are not working, so the system is not working as smart as it should be. In this case, the backup mode is to switch to the regular mode, which is either fixed time or actual. So yeah, that's the advantage of having the integration with already well-established hardware.
Would the city let you test your code or your project on the real streets, like for real?
Okay, this is actually one of the main challenges, because each city wants to, was it tested somewhere else?
Yeah.
So yeah, it needs like a brave city to accept the first implementation, but we are almost there. I can't say which city exactly because there is no confirmation yet. But hopefully, yeah, there is one of the municipalities that they are interested and to implement it, and hopefully we can implement it there, and from there we can go further.
So when you first talked about Guelph, I thought this was an implementation. So it's only simulation.
No, again, only simulation.
Okay, I found something a bit surprising. So the right part of the table, it was 3,000 less vehicles than the left intersection, and still you found that coordinated is better than independent. Right, so 6,000 vehicles on the Guelph line, 9,000 on the Walker's line.
Yeah.
And still coordination was necessary for Guelph and less necessary for Walker.
Okay. Because as you can see here, these intersections are too closely spaced.
Okay.
So the coordination was really important here for these intersections to work, regardless
It has
of the
nothing to do
number.
with the number.
No,
Small.
it's the variations of traffic flow and how closely are the intersections. These are the two main parameters that affect the performance of the coordination over the independent.
Okay, that's an interesting observation. And my second quick question was, so when you do have many intersections and you need coordination, does error propagate? Because it's done in a cascading fashion, right? I'm not good at game theory, but if you have some error in a neighbor, and this error percentage is propagated to you, and then you take another error from another neighbor.
What do you mean by error?
هو مش error بس يعني like let's say like underestimation or overestimation.
That decision. Okay.
That decision. Error in the decision making process. Not necessarily error as in if it is a bad decision, but مش عارفة أكيد
I know it's okay.
What's your the expert with this? What do they know? It's like because it's self-learning. So if you get like a mistake or you have
Yeah.
you will
error,
correct it
like
in the next
Yeah.
situation.
you're gonna get a bad reward that makes
Exactly.
you like shift to another like
Yeah.
decision that I have.
This
to
is the
do.
importance of continuing learning in the field, not only having a fixed control policy that works forever. So it corrects itself. Even if it happens once that
Okay.
it was a bad decision or whatever, or yeah, so
Okay.
be corrected with time.
I see. Thanks.
I had two questions. One of them was already been asked about the propagation of noise or fault. But the other question is there a scenario in which Marlin can resolve a problem in certain intersection but throw away the problem to another intersection? I mean, you get mass performance in this intersection, but on the expense of having congestion in another neighboring cell that you don't assess its performance. So, I mean, or in different words, how many surrounding nodes or intersections are being evaluated with the performance metrics that you're using? Is it only the intersection that had Marlin installed in it, or the system as an overall mesh?
I got your point. So you're asking if we decide just to put Marlin in one intersection and the others are not controlled by Marlin. Again, in this case, it might not be fully coordinated because they are not operating with Marlin or they are not taking decisions using the same technique, so they can share their decision. But they can be partially coordinated, which will also by at least having information about their state. So the traffic state at each intersection. This will help, and this is one of the approaches that we tested, and we found I don't know if it's here, no? But in the main framework, I mean, so partially independent, we call it partially independent because it's again an independent in terms of the decision making. So partially because we observe the joint state of the intersection. So the results that, of course, the coordination is much better in terms of the performance and results, but again, this is better than totally independent. So it's a good question.
I meant that these nodes are smart, right, to resolve the problem locally, but what if all these smart nodes are competing with each other? So would they serve for the overall performance or the local performance? I mean, the total network, or it's only, what's the target of each
The
intersection?
target of each intersection is to minimize the delay for that intersection. But the building the models for the neighbors and considering that to take the best response action, we actually classified as, if you are aware of the game theory, mixed game. It's not fully competitive, which means that they are against each other. For example, the reward is for one agent is exactly the opposite of the other. It's not the case, and they are also not fully cooperative. They are not they don't have the same exact goal. So it's mixed game. In this mixed game, the approach that we
It's not a zero-sum game.
yeah, it's not a zero-sum game. So So they are taking the best response actions according to others.
So you said that the system depends on the transportation infrastructure in the city. So is this a standard? So can it be implemented in Japan, for example? Or?
Yeah, it works with any NTCIB. I can't remember the abbreviation for what, but the standards for the controller. So any controller works with these standards. It can be integrated with model. This, at least for now, we can actually extend it and integrate it with other standards, but we are now ready to integrate it with other controllers that are NTCIB based standards.
So for ramp meters, do you think more than in the current state, in its current state, can be implemented for ramp meters and highway control?
Yeah, as I mentioned, it's the general framework for the agent in terms of the learning algorithm, the decision making. It's designed to be really independent of the problem. The state and reward and action definitions are defined in the environment itself. So in this case, the environment, the definitions, of course, need to be changed for the state, and because it's kind of different type of interactions in the traffic flow. For freeways different than the signals that in the surface streets. So, and as you probably know, Kasra is working in this topic, so he is considering reinforcement learning for ramp metering. So the definitions for the state and action reward, and even the decision time, the decision step. And now the decision is made every second, unless, for example, for sure, I mean the minimum delay. So after the minimum green time, the minimum green time that allowed pedestrians to cross the intersection for a certain movement, after the minimum green, every second I can take the decision either to keep the green for the current movement or to switch to another movement. So the RAM metering, the decisions are different, the time step is different, and so on. But it can, in terms of learning and even the coordination between different RAM meters can be done in the same way. Even coordination between signals and RAMs in the same network can be done using the same way of coordination.
I'm sorry, this can be a stupid question for transportation. How do you know the number of arrivals? Do you have sensors on an intersection that know the expected number of cars at a given time?
You mean the data that we use to build the simulation model for them? It's for, I think the count. The city have their own methods of counting. They do it, for example, different days in the year and different times, and then they have the average and report it. So they use someone who's count the ratios, our cameras, and then post-processing to this camera feeds and do the counts. But at least for us, we got it from City of Toronto.
Okay.
Sheets from City of Toronto that has all the turning counts and through counts and so on.
And if it's implemented in real life, it will keep track of these counts?
No, in real life, no, of course it's a good question. We will use cameras, as I said, for now. But again, it's developed to this, the arrivals or the queue length information is an input to the system. So whatever technology can give us this information, it will work. Of course, the more accurate this information is, the better the system will work. So for now, it's the video cameras, and we actually know certain vendors that we will use the cameras. But maybe later on, the connected vehicles, when vehicles can talk to the infrastructure, will of course give us better results. Because in this case, we can track each vehicle, and we know the exact delay or waiting time for the vehicle. So
you call them vehicle networks?
Vehicle to infrastructure or vehicle, connected vehicles. Where the vehicles have the devices that can send speed, position, and to the infrastructure or to the traffic light.
Do you know if the city of Toronto use any smart traffic control systems or just?
They have about 300 of the intersections operated by Scoot, which is the one. This one.
Okay.
So Scoot, they had a request for proposals 2 months ago to replace schools,
Okay.
or at least to try to solve the issues that they are facing with school. The human intervention thing that it requires training for people who are operators who are working in the city to have identify the different parameters, because it's kind of complex system and it's centralized. This is the main limitation of the system. It has to come, the instruction to the intersections or the operation to the intersection comes from a traffic management center, which needs communication infrastructure and network that's expensive. And
I ask this question because sometimes when I move in the city, I notice that some of the roads, like Spadina, for example, because I move it every day, like they design the traffic lights to make the car stop at each intersection. I'm not kidding. It's like stop at each intersection, even with the car. It's not by bike or something. So, is there any insight behind this?
And
I
Transit signal.
yeah.
There is a
Oh,
streetcar.
okay. If there is a
There
streetcar,
is a
as I mentioned, they always give the priority to streetcars and to buses and so on. So this might be the reason. Because Padania has streetcars, so given that the priority is for transit, so yeah, this affects
Extend the delay.
excessive delays for cars. So that's why we hope that we can do some work in the people signal priority thing, but again, it depends on the technology that can give us the information of the number of passengers in each transit vehicle.
Okay, so if there are no more questions, maybe I'll ask just one other small one.
Sure.
So this sounds like the next big thing in traffic controllers and traffic management. So based on your experience, what do you think the next one will be like? What do you think is still left to implement?
Again, the connected vehicles will make this system work much better. And yeah, I think the future is to integrate the concept of connected vehicles and use the big data, also the techniques and methods to deal with also the big data that's coming from vehicles to enhance the operation of the traffic signal control system.
Okay, so smart cars with smart traffic lights.
Exactly.
And people priority.
Yeah.
Okay, so please join me in thanking Dr. Samah El-Tantawy.